Feel free to interrupt at any point. Happy for this to be more of a discussion than a lecture. So, and of course, I'll emphasize it's not just me. There's several people. You can see the names here, both at Sydney and some colleagues at MIT who've kind of contributed to the work in this over kind of many years. Kind of been working towards this material. So the title is kind of Robust Machine Learning and Data-Driven Nonlinear State Estimation. So I want to kind of talk, I guess, about how those two kind of concepts interact and how they kind of come together in some recent work of ours. So I'm going to start with something that's probably well known to many of you, but perhaps not all. So I'll just kind of start with a bit of a background to what state estimation is, and particularly from the kind of control theory perspective, what we think of as state estimation and the particular challenges that arise when you're dealing with nonlinear dynamical systems. Then I'm going to shift gears a bit and change topic to robust learning of dynamical systems. And I'll kind of define a bit more precisely what exactly I mean by that, and talk about some of the recent kind of model architectures we've been working on that kind of have built-in guarantees of things like stability and robustness. And then I'll kind of come back and show how those two come together. And in particular, we use the model architectures that we develop in this section to provide a new perspective or a new way of solving the state estimation problem, which I think has some really interesting kind of potential. It's kind of a different view on solving the state estimation problem, I think. Okay, so let's get started with state estimation. So I guess in general, as many of you will know, models for physical systems typically take the form of ordinary or partial differential equations describing rate of change of some state. In physical models, these are typically positions, velocities, pressures, currents, and so on. But more generally, you know, there's lots of different dynamical systems that we can associate the concept of a state with. Roughly speaking, the state of a system is sufficient information to predict its future. This might be to predict its future perfectly in the case of a deterministic model, or in a stochastic model, it would have what we call the Markov property, which is that if you know the state, then the future is conditionally independent of the past. So it's basically a summary of all the relevant information, kind of sufficient statistics for from the past for knowing the future. The reason that control engineers are very interested in the concept of a state is, well, there's many reasons, but one of them is that when you're trying to control real systems, it's very, very rare that you can achieve perfect measurement of the full state. So usually you only have some sensors available, and these will generally give somewhat noisy measurements. So the problem of state estimation is to estimate the true state of a dynamical system given only partial and noisy information. And there's this kind of general problem appears in many, many contexts: feedback control, as I mentioned, but also areas like kind of fault detection, process monitoring. Simultaneous localization and mapping problem in robotics can be considered as a state estimation problem, and many others. And I know that researchers within the DARE Center are working on many problems of this nature. Okay, so I guess in the kind of control community, a common structure for a control system is as follows, this kind of block diagram here. So you might have a, this block here represents some kind of true dynamical model. Here I'm writing it as a set of nonlinear ordinary differential equations, kind of ignoring noise terms and so on for the moment, but of course they can be present. But this system has some input which we can control and some output which we can measure. and it has some internal state which we don't have access to. The typical structure of a state estimator is to take some copy of the dynamics of the model. So you would say, I'm going to build my state estimator by first having some kind of model prediction, but then you also have some kind of correction term that looks at the difference between what the sensors are telling you. So this is the measurements that are available, and what you predict the output should be if your model was correct. And this kind of gets fed back, and you produce some internal estimate of the state, which can then be used for control. So for example, the famous Kalman filter is an example of this structure. More generally, this structure could be called a Leuenberger observer, and there's many kind of different realizations of that. I guess the Kalman filter is probably the most well-known example of that. And perhaps the most, well, actually the first ever practical application, and still possibly the most famous, would be the Apollo moon landing. So the extended Kalman filter, in fact, which is a nonlinear state estimator, its first ever practical application was in the navigation system of the Apollo moon mission, and that was kind of a very fortunate serendipitous kind of occurrence from when Rudolf Kalman just happened to visit NASA and give a talk about this filter he'd been working on, and it turned out to be exactly what the NASA engineers working on this navigation problem really needed, and so they basically plugged it in and it got used right away. Okay, so the Kalman filter, as I mentioned, this is I guess the most well-known and widely used type of state estimator. The Kalman filter is specifically designed for the setting in which you have a linear dynamical system with some additive noise terms, which are zero mean, IID, and have known covariances. And then the Kalman filter takes the form I described before, where you have some kind of prediction based on the model of your process, plus some kind of correction term, which is based on the difference between the measured output and what your kind of predicted output would be. If X hat was the true state, then this would be the true output of the system if there were no noise terms. And this can be interpreted in many ways. I haven't added the computations here, but the gain matrix LT can be pre-computed using the Riccardi equation. There are many interpretations of the Kalman filter. It can be seen as a Bayesian estimator. It can also be seen as a minimum variance estimator, but the best unbiased estimator in a minimum variance sense. It can also just be seen as solving a particular recursive least squares problem. And I think the nice thing about the Kalman filter is it really satisfies kind of the holy trinity when it comes to state estimation problems. It is in several senses statistically optimal. It is under very mild assumptions guaranteed to be stable, which means that basically no matter what happens, estimates aren't going to diverge widely from the true state. And as long as if noise terms are small or tend to zero, then it's guaranteed to converge to the true state. And it's also very simple to implement. It's just a few matrix vector operations, and it's very, very easy to implement in any kind of embedded computer. When it comes to more complicated systems, things get much, much more challenging. So I guess there are two big, going from the setting of the Kalman filter, the two big things here are, on the one hand, it's linear dynamics, and secondly, it's finite dimensional. In many cases, the real system that we are trying to estimate, it's not finite dimensional, it's infinite dimensional. So the dynamics would be governed by partial differential equations, which corresponds to a kind of an infinite dimensional state space. And the dynamics are almost never actually linear. So both of these pose very, very significant challenges for state estimation, and achieving the combination of statistical optimality, stability, and computational simplicity is pretty much impossible. So when we have systems governed by PDEs, the most common approach is to kind of go through a kind of a sequence of steps. You take the PDE. The first thing you do is discretize the state space. So basically you do some kind of POD, Galerkin, finite element method to construct a finite dimensional approximate basis for the state space, basically some set of kind of basis functions that you can essentially project the PDE dynamics onto, which will represent the dynamics sufficiently well. Then you take that gives you then an ODE model, or which you can then discretize in time as well, if you like. And then you design an estimator for that ODE model and apply that. More recently, this recent work in kind of observer design for PDE systems has flipped that. So more recent approaches might look at the problem of designing a stable observer or a state estimator for the PDE itself, and then discretizing the result of that process. So then what you get is an observer which is somehow kind of independent of the particular grid or the particular basis functions. It's a PDE state estimator, and then you discretize that, and that has some benefits as well. In some cases, these can actually be shown to be equivalent. Secondly, kind of moving on to the issue of nonlinearities. Of course, most real dynamical systems are nonlinear. In robotics, we're very often dealing with non-Euclidean state spaces. So, you know, in robotics, you're very often dealing with things that are rotating in 3D space. And so your state space might be the special orthogonal group or the special Euclidean group, not a real vector space. You've often got nonlinear forces due to things like friction, or in other classes of systems, chemical reactions are typically nonlinear in their dynamics. And then especially in robotics, but many other fields as well, you're typically dealing with nonlinear spaces when you're dealing with many types of sensors. So things like cameras, if you have a camera looking at a 3D world, then the relationship between points in the 3D world and the image plane of the camera, that's a nonlinear relationship. It's a projective relationship. So you need to be able to deal with all of these issues. And I guess as I was kind of saying before, in these cases, it's generally impossible unfortunately, to achieve all three of those properties that we would like of statistical optimality, stability, and simplicity of the algorithm. And most methods, I would argue, kind of pick one of these or maybe two of these to focus on trying to maintain. So the EKF, the extended Kalman filter, is the simplest approach. It really focuses on maintaining simplicity, I guess. In a sense, you get statistical optimality under very nice conditions of very low noise and good guesses and so on. But stability of the EKF is extremely hard to establish, and still after 50 years of research, it's still basically an open problem of when an EKF will be stable. And it's not hard to come up with quite mild situations in which an EKF goes crazy. At the other end of the spectrum, you have methods that really, I guess, focus on trying to achieve statistical optimality at the expense of simplicity. There you've got things like Monte Carlo methods, like particle filters, but also more optimization-based methods, like moving horizon estimation or fixed lag smoothing, which is common in SLAM now, algorithms like the graph SLAM algorithm. And these can be, in a certain sense, approximately statistically optimal, at least in the limit as the number of particles goes to infinity or the length of your horizon goes to infinity. But also, as the number of particles or the length of your horizon goes to infinity, you would basically go towards an infinite dimensional optimization problem that you need to solve in real time. So this then becomes very, very, very challenging from the computational perspective, especially if you need it to operate in real time for a dynamical, for something like a UAV or a ground vehicle. So then there's a third category which is studied in particular in nonlinear control theory. It's especially in the context of feedback control, it's quite a strong approach. It basically throws out statistical optimality and basically gives up on statistical optimality, but tries to achieve the other two. It's a simple observer structure similar to the Kalman filter, and at least in some cases, you can prove that it will be globally stable, but generally you have absolutely no guarantees of statistical optimality. And I think the methods we're doing is kind of more in this category, although we have approaches that might help to bring it somewhat towards kind of good statistical properties as well. So that's kind of a brief overview, I guess, of the lay of the land on nonlinear state estimation, at least from the control systems and robotics perspective. So unless there are any questions on that, now I might kind of shift gears to the second part of the talk, which is kind of introducing our recent research on kind of robust learning in the context of dynamical systems. Okay, yeah, I think we'll go on to that then. Okay, so many of you may have seen images like this, particularly in the context of the recent craze around deep learning, maybe not so recent, last 10 years or so. So this is the output of an image classification model. Here you have an image of a pig, and this is the label that the classification system says, yes, pig, pig, that looks good. Then it turns out that for most of these sorts of classification algorithms based on deep neural networks, many of them are very fragile in the sense that you can add a tiny perturbation. So if you add 0.005 times this random looking noise pattern, you get this image here, and to the naked eye, you can't really tell the difference between these two because it's only a very, very small difference in terms of the noise, but it fools the classification algorithm into thinking this is an airliner. So this is this shows there's really still an extremely big difference between what deep learning based classification algorithms do and what the human brain does, because no human, no matter what, would think that this is an airliner. So there's really something fundamentally different, and dealing with this problem, dealing of kind of fragility, or especially to what are called kind of adversarial examples. This has been a pretty significant area of research in machine learning over the last 5, 6, 7 years or so. So this is what you could call extreme sensitivity of the output of the network to the input of the network. So you have a network that works well on a particular data point. A very, very, very tiny change in the input leads to a huge change into the output, a completely different kind of category of labels. And so this sensitivity of outputs, extreme sensitivity of outputs to inputs, is, I guess, trying to control this or trying to reduce it is what we're going to think of as robustness of a neural network. So how can we quantify this? We quantify this with something called a Lipschitz bound. So any Lipschitz bound is quite a common tool in machine learning to understand robustness. So basically any sort of function or operator which produces outputs given some input. So here we can think of X as being the image and H of X as being the label that it predicts. We can call such a function like this Lipschitz continuous if there exists some constant gamma such that the difference between the outputs of the function is less than or equal to gamma times the difference between the inputs. So this is kind of a gain. It's almost like the kind of the volume control on the network that if gamma is small, then small differences in inputs don't result in small differences in outputs. If gamma is really, really large, then at least it may be the case that with very small differences in inputs, you can get very large differences in outputs. And roughly speaking, at least for scalar functions, gamma is a bound on the slope of the function. But this also makes sense in higher dimensional spaces, as long as you just have some norm defined on the input and the output spaces. So in machine learning and control, Lipschitz bounds appear pretty much everywhere. They appear in formal, formal proofs of robustness to adversarial examples, proofs of generalization to examples outside a training set. Also some recent interesting work on learning algorithms that will guarantee privacy of the, some kind of input space. So if you have if this X, you have some network that produces some output given some input, so that where the input itself might be private, but the output of the network is made public, then what you want to maintain privacy in terms of the input data is that small changes in the input data shouldn't result in big changes in the output. And so you can actually prove differential privacy of mechanisms constructed with neural networks via Lipschitz bounds like this. And I guess more relevant for my own research background, and especially problems in robotics, like the kind of control of walking robots that Gillard mentioned, which is motivating kind of a lot of my research, stability guarantees for feedback systems and nonlinear feedback systems are very often framed in terms of these kind of gains of various operators in a loop. So in particular, if you have a feedback between multiple systems, if the total product of all the Lipschitz bounds is less than 1, then you can achieve stability of that feedback loop. So this understanding and perhaps controlling the Lipschitz bounds of neural networks is a very useful thing in many different contexts, kind of a good way of regularizing a neural network. But unfortunately, computing the Lipschitz network of a neural network has been proven to be NP hard. So it's, it would be nice to be able to exactly compute Lipschitz bounds and use them as some kind of regularizer. But unless we establish that P equals NP, we're probably not going to be doing that. So instead, what we do is we work with some kind of upper bounds for the kind of optimal Lipschitz bound. But it turns out, as you'll see in some of the examples that follow, these upper bounds, although in a certain sense they're kind of based on fairly crude ideas, they actually give pretty tight results in cases of interest. So so let's have a look at that. So if we'll start here with a very, very simple example. So this is a scalar function of a scalar input. So this is really just using a neural network purely for curve fitting, right? No noise, no nothing. It's kind of the simplest possible input-output learning task you could think of. And if you really wanted to do this, you wouldn't use a neural network for it. There's much simpler things you could do. But here the data is the blue line, which is actually a sum of two sinusoids. So you got kind of a low frequency sine wave and then a high frequency sine wave, which is a 5 times faster frequency. And then what that means is the true maximum slope of the blue function is 2, but then we learn a neural network using the methods, which I will present later on in the talk, and we use our bounds to say this neural network, the output should have a maximum slope of 1. And the result is the kind of orange curve. And the actual, if we look at the actual slope achieved by that network, we've told it you bound your Lipschitz constant, your slope has to be less than 1. And it's clear that to best fit this function, the slope should be kind of as big as possible, because you can fit it perfectly if you can get a slope of 2. So what the method actually achieves is a slope of 0.96. So the gap between the achieved slope and the bound on the slope is only, let's say, 4%. On the other hand, if you look at kind of more, I guess, existing methods of bounding the Lipschitz constant of a neural network, which is basically just taking spectral norms of individual weight matrices, it's 16 times worse. So it would estimate the slope of this orange function to be 16 when actually it's less than 1. So we have kind of many orders of magnitude better, tighter bounds on robustness than the commonly used way of regularizing neural networks. Another example, so this is slightly more interesting from an applications perspective, although still quite small scale. Many people will be familiar with the MNIST image classification data set. This is quite famous, goes back to the 1980s, I guess. It's handwritten numerical digit recognition. So what I'm plotting here is some methods that we've been working on, which are the crosses against some alternative methods. And the two axes of these plot, the horizontal axis is the Lipschitz bound, which, as you said, kind of represents the sensitivity or robustness of the model. And so basically, if you can achieve a smaller Lipschitz bound, it means you're less sensitive to these sorts of adversarial examples, less sensitive to noise perturbations. So we'd kind of want to be ideally to the left. And then this is the error on the test set from that data set. So you have the MNIST data set has a specific training set and a test set. If we look at the test error, obviously you want that to be as small as possible. So basically what you want is to be towards the lower left. Here, so our results are here with different prescribed bounds. You can see we're saying the Lipschitz bound should be just this gamma less than infinity. It just means it should be bounded, not any particular bound. And then we have various numerical bounds. There's a competing method called Lipschitz margin training, which doesn't precisely bound the Lipschitz constant, but it gives you a kind of a parameter that you can tune, which tries to do a similar thing. And this is the circles here. So you can see, again, you see a kind of a trade-off curve between Lipschitz constant and test error, but it's kind of strictly worse. You prefer to be towards the lower left here. And then if you just look at a regular neural network, so completely unconstrained, you can see you can achieve kind of similar test errors. Around 2% is quite typical for fully connected networks on the MNIST dataset, but with orders of magnitude higher sensitivity than the bounded networks that we have. So basically you can have something like 100 times worse sensitivity to small perturbations if you use just a standard neural network compared to our models. And this is the kind of thing that you see. So this is just some examples of perturbations. So you have here that in the horizontal row, these are the characters. And then if you go down each column, it's actually looking at the adversarial examples that it builds to try to confuse the network. So kind of in order to confuse the network about whether or not this is a 3, it actually has to turn it into a different number. So it has to actually go from a 3 to an 8 or from a 7 to a 9. Here again, a 3 to an 8. This is probably a 0 to an 8 or something. So it's it's very, very different to the example we saw before of the pig and then what still looks like a pig but gives the wrong label. Here, in order to get our networks to give the wrong label, it really has to change the image so significantly that it actually does look like another digit. So that's it's kind of eliminated that extreme sensitivity to small amounts of noise. We can see similar results or a kind of comparison of robustness numerically here. This is kind of a similar set of results, but presented in a different way to the previous slides. So here we're just looking at a bunch of different networks, and then how does the test error accuracy change as you allow perturbations of different size, those kind of noisy patterns. If you have a different bound on how large those can be, what effect does that have? And you can see that, for example, when we have lower Lipschitz bounds, then you sacrifice a small amount of test like nominal accuracy, but you get a much lower slope. So as you get larger and larger perturbations, the accuracy kind of rolls off much more gradually than it would with the more standard networks. So the black lines are just the regular unconstrained networks, which kind of go up to about 50% accuracy with a perturbation of around 5, whereas with a strong Lipschitz bound, you can get double the perturbation with even higher accuracy. So this is some, I guess, just some motivation that what we're doing kind of does have real impact in some classification tasks. This is just for image classification though, very static scenario. So you might be wondering, what on earth has this got to do with state estimation? So we'll go a little bit in that direction, and we'll start thinking about Lipschitz constants of dynamical systems. So we think of a dynamical system it really is still just kind of an input-output mapping, but now the inputs and outputs are signals. They're not images, they're not vectors, they're not they're not elements from a finite set of classes. They're signals, and these might be signals on a particular signal space, for example, L2. And what we're trying to learn is a mapping from one signal space to another. And then we can still talk about Lipschitz bounds of that mapping. So our mapping from inputs to outputs can still have the same sort of Lipschitz bound, but here the norms are signal norms. So we might have continuous time models, and the norm is the kind of integral L2, or we might have discrete time models, and our norm is the sequence L2. So it's basically the sum of the squares of the signals themselves. There's a connection here to robust control theory, which is that this gamma for a linear dynamical system is what's called the H infinity norm of the system, and trying to bound this gamma or keep it small is a problem called H infinity control, which is kind of there was a very significant body of research in the 1990s and early 2000s on how to do that effectively. So this is kind of a fairly well-established paradigm in control theory to think about signal norms in this sense, but we're going to use this to talk about robustness in the context of system identification, learning dynamical systems, and then we'll come back to state estimation. Another concept that we need to introduce, so not so much representing sensitivity to differences in inputs. So this Lipschitz bound represents sensitivity to differences in inputs to the model, but a dynamical system like this typically will have inputs, but it will also have initial conditions. And so another concept which I guess quantifies sensitivity to initial conditions is what's called contraction, or a very closely related concept of incremental stability. So what is contraction, or when do we say a dynamical system is contracting? Basically, if no matter where you start the initial conditions, all solutions of the system converge to each other. And so you can have either continuous time, so ODE models, or discrete time models, it doesn't really matter. But basically you have this property that if you have some difference in the initial conditions of the model, and then you look at the difference between the solutions over time, then this is actually the solution over time actually converges exponentially. So there's some overshoot constant k, and then e to the minus lambda t, where lambda is a positive constant. So basically you're saying no matter where you start your initial conditions, eventually all initial conditions converge to each other exponentially. And under kind of fairly mild conditions, any dynamical system with finite Lipschitz bound is also contracting. So these are kind of the two concepts that we need for our work on dynamical systems. What's the right way of thinking about contraction? I guess, what does it get you? Roughly speaking, I would say that for nonlinear dynamical systems, contraction is the kind of formulation of stability that makes nonlinear systems most like linear systems. So basically, there are many nice properties of stable linear systems. For example, that initial conditions are forgotten exponentially. If you have a bounded or decaying input to the system, then the output will be bounded or decaying in a similar way. If you have a periodic input to a system, then the output will be periodic, and you have kind of natural robustness in various other senses as well. So these, when you have a contracting nonlinear dynamical systems, all of these, all of these remain true. If you have nonlinear dynamical systems with other kinds of stability, like Lyapunov stability, that's not necessarily true. You can have a stable system, but even a small perturbation to it makes it unstable. So contraction is kind of a robust form of stability for nonlinear systems. Okay, so let's have a look at some examples of using these concepts in dynamical system learning or system identification. This is what we'll show on the next slide is a data set that was collected by some researchers in Belgium with the assistance of the Belgian Air Force. They didn't buy an F-16. They borrowed one or were assisted by the Air Force. So what they were actually testing here was, or trying to model, is the vibrations in the wing, basically in response to some impulse. So a wing is, actually fairly flexible and highly resonant, and understanding this resonance and flexibility, it's quite difficult to model exactly. And so they wanted to do some experiments to test this and build models of this. So basically they had a whole bunch of accelerometers along the wing, and then they applied some forces at various points of the wing and recorded the response. So this is kind of a benchmark data set for nonlinear system identification. It's seen as very challenging because it's very high dimensional. It's really a continuum mechanics PDE. It's highly resonant, and it's highly nonlinear as well. So again, we have kind of a similar plot to the one I showed before, comparing. So again, yeah, I don't really have the acronyms explained here, but basically this is the test error, normalized root mean square error on a test data set, and then this is the Lipschitz constant. Don't worry about the triangle ones. These are another model class we were looking at, but basically the model class that we're proposing is the diamonds, and then two widely used model classes for dynamical systems in machine learning. One is LSTM, also called long short-term memory, and another one is just a generic kind of vanilla recurrent neural network structure. So what you can see is with the robust models, you can achieve as good or better test error, so in terms of how far down the graph we are, but significantly further to the left, even kind of orders of magnitude lower Lipschitz bound, so sensitivity to perturbations to these standard models, LSTM and RNN. Okay, so that's kind of, I guess, some results and some motivation. So now I'd like to present briefly, I guess, kind of the main technical ideas. So what are these bounds? How do we get these bounds? Where do they come from? So I've kind of claimed that they're better than what has come before and that they're very useful. So how do we actually achieve these, or what's the model structure look like? So for the image classification results, what I actually showed was not a standard neural network structure, although we can do similar bounds for those as well, but it was actually a structure called an equilibrium network. So this is the kind of structure here. If you're familiar with neural networks, you'll know that typically they're constructed from compositions of matrix multiplications, or generally kind of linear operations with scalar element-wise nonlinearities. So this is the same general structure. You've got some weight matrices here, WU, and a bias vector here, and you've got a scalar element-wise nonlinearity.
The difference is that you've got Z appearing both here and here. So it's not just a kind of input-output model. The output of this model is actually the solution of an implicit equation. It's sometimes called can be called an equilibrium network because it can be considered as finding equilibria of dynamical systems, either given in discrete time or continuous time form, sometimes also called implicit deep models. It can be shown that this structure of models basically includes almost all previous neural network structures as special cases. So for example, just a standard multi-layer feed-forward network can be represented as a single layer equilibrium network with a weight matrix, which is just kind of off diagonal in this way. So you can just kind of, if you just go through and think about the matrix multiplication, it just ends up being a feed-forward neural network. And you just have one kind of shifted off diagonal set of weights. If you have another shifted, the next diagonal down of weights, then you get what's called a residual network or ResNet with skip connections, and you can have other kind of common structures as well within this framework. So it's quite a flexible structure. And then we go beyond that to the dynamical model, and here we use kind of a framework which is common in robust control theory, which is to consider nonlinear models as interconnections of linear and nonlinear components. So we think of this feedback interconnection here where G is actually a linear state space model given by these equations here. And then sigma represents the scalar element-wise nonlinearity. So here we have W equals sigma V. This is just a activation function applied element-wise, but then W appears as inputs to all of these equations. Here, this is the state equation, this is the output equation, and this is the bit that goes in the feedback loop. But you notice V depends on W and W depends on V. So you do actually have an algebraic loop here. And so again, this is, it's kind of a recurrent model with an equilibrium neural network as part of its internal structure. So actually this structure can include almost every class of recurrent neural networks that has previously been considered. So how do we show these kind of incremental properties? I mean, incremental in terms of incremental meaning kind of differences between solutions. So Lipschitz bound is studying the response to differences in inputs. Contraction is studying responses to differences in, excuse me, in initial conditions. So this is our model structure that I showed on the previous slide. What we do is we look at differences between pairs of solutions of this model. And if you have two different models, and if we just look at the contraction case for the moment, we just assume all inputs are the same, the biases are the same, they're fixed, but what we've got is different initial conditions and different values for W. So if we look at those differences, we can just write kind of a simplified linear model where delta is kind of XA minus XB, delta W is the same for W. And this is fine. This is just a linear model for the for this block, but somehow we need to deal with the increments of the sigma block. So what do we do with this? So we have a look at the structure of common activation functions, and we notice that in almost all cases, these activation functions are monotonic and slope restricted. So basically if you go from left to right, they're increasing, and there's a particular bound on the slope, which is, in most cases, the bound is either 1, or you can easily rescale the activation function so it is 1. So we'll just say they're all monotonic and they all have bounded slope of 1. And that's basically all the information we'll use about the activation functions. That monotonic slope restricted property can be written like this. So basically the output, two outputs, difference in outputs over the difference in inputs is greater than 0. That says it's monotonic, and is less than or equal to 1. That says it's slope restricted. So this is that property expressed as kind of two inequalities. You can actually just rearrange this a little bit and write it like this. So this is just kind of multiplying through by VA minus VB squared and doing a little bit of manipulation. So this is now what we would call an incremental quadratic constraint for the relationship between the input and the output of that nonlinearity. This constraint holds for all possible pairs of V and W. And it also holds for all activation functions in the network. So we can actually kind of add up combinations of these with some different weights. So we actually introduced this new matrix here, lambda, which is a diagonal matrix. Basically, what this means is you just take all the different incremental quadratic constraints for different activation functions, you multiply them by a positive constant, and you add them all up. And these positive constants, they're kind of like Lagrange multipliers in a condition. They're kind of extra terms that you can tweak to get tighter bounds. And then we do another kind of trick, which is to observe the multiplier into the model equations. That's just so that we don't have kind of products of lambda and d appearing here. So we end up with this now incremental quadratic constraint here. And so this holds for all delta x and delta w. And then the way we achieve this kind of guaranteed stability, contraction property of the model is we kind of think of three different terms. This is this kind of we call it a Lyapunov function decrease term. So it's basically saying that from one time step to the next, in terms of a certain inner product defined by a matrix P, solutions get closer together. So this is what we want to be the case. We want the system to be contracting. Then we have another term here, which kind of is, it's like a Lagrange multiplier term on the linear dynamics. So for solutions of our system, this term goes to 0. So that disappears. And then we have all of our incremental quadratic constraints for all of our activation functions. And for any monotonic slope restricted activation functions, we know that this will be non-negative. And so we have this term vanishes, this term is non-negative, which means, and then we've got an inequality sign here, which means that for all solutions of our system, we have this in terms of this metric, solutions are getting closer and closer together. So actually, if we can establish that this inequality is true, we can guarantee that our model is contracting. And we can do similar things for the Lipschitz bound as well. Now, this is just a homogeneous quadratic inequality. We can rewrite this as a linear matrix inequality. So we can rewrite this, kind of collect all the terms into a big matrix and just say this matrix should be positive definite. And this would be, you know, if we were doing robust control theory like 20 years ago, this is where we would stop because we've expressed it as an LMI, linear matrix inequality, which can be solved. It's a convex representation. It can be solved using semi-definite programming. But the semi-definite programming is great. We use it a lot. I love it, but it doesn't scale very well to really huge models. So typically, if you've got more than about maybe 200 or 300 states in a model and activation functions, the solving a semi-definite program like this gets quite nasty. And so what we do now actually is we go one step further and we say, well, hang on, let's just think of this as a big matrix, which should be positive definite. We can just write that as, let's say, VV transpose, where V is just some totally free matrix and epsilon is some small positive constant. So for any matrix V, VV transpose is definitely positive semi-definite. And then you just add a little bit to make a positive definite. So that's our H. And now it turns out, if you look at the structure of this, if you know H, you can actually extract all the model parameters from that. So we can actually just, from a completely free matrix V, we can construct this parameterization of kind of robustly contracting and Lipschitz bounded dynamical models. And that means that we don't actually have to impose, there's no constrained optimization at all. We just have a totally free matrix variable that parameterizes everything that we're doing. And then we can just learn these models using any unconstrained optimization method. So stochastic gradient descent, or it's kind of variants like accelerated gradient methods, Atom, all of these tools that have been developed in the machine learning literature, we can just plug them in because we have an unconstrained representation. Okay, so that's kind of how it all works. I probably went, I think it's challenging to get kind of all the detail there, but that's hopefully the main ideas have kind of come across a little bit. So let's now circle right back around for the last couple of slides. How does this then help us with the nonlinear state estimation problem? So here we kind of, as I presented at the very beginning of the seminar, a typical way to try to solve the nonlinear state estimation problem, let's say for a discrete time dynamical model, is to take a copy of the dynamics and add some kind of correction term. But this is, and this includes things like the extended Kalman filter, but designing the correction term to achieve global stability, this is very challenging and is highly problem dependent. We don't really know how to design this term in a general sense. So let's think about it another way. Rather than taking this model, rather than taking this kind of prediction plus correction term, let's just write our state estimator just as some dynamical system. We call it FO for observer. It has the state estimate as its own internal state, and as inputs, it takes the true system's input and output. And the main idea of thinking about this from the point of view of designing, from the point of view of contracting models is this kind of thinking about just designing the observer directly can actually be simpler than designing a correction term. So let's think about if we had the property that this observer is contracting, which means that any two initial conditions converge to each other. And if it has the additional property, which we call correctness, which is just a relationship between some functions, what this means is actually that the true state is a feasible solution of the observer, then we get a guaranteed state estimator. So how does that work? Basically, the proof is that on the one hand, all solutions converge to each other. And secondly, the true state is one solution of the system. So if all solutions converge to each other and the true state is one solution, then all solutions converge to the true state. And so what we need then is to be able to guarantee these two properties. This one we've just guaranteed through the construction I gave on the last few slides. So by definition, our model is contracting. And this one is actually just a supervised learning problem where we have the function FO, we have some known inputs to it and some known outputs we want it to match. And so we can just try to match this at as many data points as we can. And then, so the basic procedure is, rather than trying to design this correction term, we just need to sample some data set. So we just sample a bunch of possible states and inputs for our system. So these are kind of snapshots of the dynamics. Then we just compute what the model output and the model dynamics are at each of those points. So this could be using whatever simulator or solver we have for that model. And then we just have a supervised learning problems to solve where we're learning over the space of contracting dynamical systems. And this is, I think, a completely new way of designing observers, but it reduces observer design for complex nonlinear dynamical systems to a simple supervised learning problem if you've got the right model parameterization. And just as an example of we're still working on lots of different applications of this, but one example that we've been working on recently, this is a relatively simple but still interesting semilinear reaction diffusion PDE. So it's unstable. This is the reaction term here, which is nonlinear, and it's nonlinear, unstable, infinite dimensional system. And so this type of model with this kind of reaction term actually appears in combustion models, models of chemical reactions, and also models of real neuron spiking dynamics, not artificial neurons. And so this is kind of a nice test case. And just to show that it does kind of work, this is, this figure here, what I'm showing here, the first plot here, the horizontal axis is time, and the vertical axis is the state. So this is a spatial state. So it's a partial differential equation. It has a spatial state. So this is the spatial state, and this is the temporal dimension. And what we're simulating here is you've got the PDE in the middle, and you've also got some kind of random forcing terms on the boundaries. So that's why you get this kind of random fluctuations at the boundaries that kind of filter through into the middle of the domain. This is the dynamics of our observer trained using the method I've just described. And we're assuming there's a single measurement in the middle of the domain. So you can just measure at a single point, and you don't have any measurements anywhere else. And you can also measure the inputs at the boundary. So you've kind of got information at the two boundaries and at the middle. And if you see what happens, the observer over time, it starts completely wrong, but relatively quickly it converges to basically the same as the true state. And then if you look at the error or the difference between these two over time, you can see what's happening. So basically in the middle where you've got a sensor and on the boundaries, the error goes to zero very quickly. But on the other states, it takes a little bit longer, but it's still converging over time. So we're able to do purely just from snapshots of the model, we can build a stable state estimator for a nonlinear infinite dimensional system. And so that's it. That's my last slide. I thought finished with a pretty picture rather than a summary slide. And I notice I've run right up against the time limit as well. So I apologize for taking up all the time. But I'm happy to stick around for questions if other people do have time, but I also understand if people need